What's going wrong? Why can't I see? What is happening with YouTube Studio? Uh-oh. Let's refresh again. Interesting. I think that's why. We have to reset. Switch accounts. Okay. I think that's it. There we go. Now it's working. Okay, hopefully it's not choppy like last time. I changed my bit rate. Yeah, I think we're fine. Okay. I need to keep this open just in case it gets bad. Okay. Cool. Where are we off to? Median of two circuit arrays. Understand why we do. Looks like we're chilling. It looks like we're chilling. Okay, so we need to solve this first. How do we solve it? We need to partition the arrays. Okay. Oh my gosh. Okay. Oh no, that's the wrong way. Okay. Alright, the stream's pretty healthy, so we are chilling. Let me turn that off. Okay. Okay. So the left pointer is 0, the right pointer is length 1, half is total length plus 1 divided by 2. We have to do less than or equal to here. That's the thing that I need to figure out why we do. Okay, it's actually, we need to walk through this again. So length 1, we need to keep length 1. So we need these three because we want to run binary search on the smaller array. So this is to help us determine which one's smaller. And then this one we need total length to determine we need total length to determine the halfway point. And then we have a right and left pointers, and obviously we need this for our left or right pointer. Now this is the problem. I don't know why we need to do less than or equal to. So that's what we're here to figure out. And partition 1 equals no equals left right minus left equal to. So half minus partition 1. If the left partition is too long, what happens? What happens when the left partition is too long? Left partition. So if the left partition is too long, we need to make it smaller. So right equals middle minus 1. Let's see. Middle. Oh, sorry, partition, not middle. 1. Partition 1. Yeah, okay, this is right, but I don't really know why. Oh, never mind, it's not right. What is this rounding error? That looks like a min val. Why are we returning? I'm doing something wrong. Left 1, left 2, half minus partition 1. Length 1, length 2, nums 1, nums 2, okay. Expected. What are we doing? What are we doing? We're returning 0 for 0. Oh. Let's see if that changes it. Yeah, there we go. Okay. So let's go through a scenario here. These scenarios are too easy. These are like happy paths. Yeah, I don't. Okay, nums 1 equals nums 2 equals. So we're going to calculate length, that's fine. So we're going to have our pointers there. This is going to be partition 1. Oh wait, is it? No. This is going to be partition 1's pointer. Yeah, that's going to be partition 1's pointer. And then half would be 6, so 6 half 6 minus 3, so 3 will be partition 2, so they'll both be in the halfway points, so they'll be pointing to, it'll be 5 divided by 2, which integer division would be 2. So they'll both be pointing here. Left 1 equals partition 0. So neither of these would be the case. So they would never equal these absolutes. Partition 1 minus 1. So left 1 would equal that. And then right 1 would be equal to this. Left 2 would be equal to that, right 2 would be equal to this. So is left 1 less than or equal to right 2? Yes. Is left 2 less than or equal to right 2? Yes. Maybe this was not a good example. Yeah, there it goes. Okay. I think it'll be easier to ask GPT this. Oops. Reload. Okay, what the heck? I think it's just time to delete. Okay, can you explain this? This goes an implementation of the algorithm to find the mean of two arrays. The algorithm efficiently combines two arrays without actually merging them. The key to this idea is to use binary search to partition the arrays such that the elements on the left partition. Yep. Initial setup. Yep. the binary search is set up with left starting at 0. Half is calculated at total length. Yep. Inside the loop. The loop? What the heck? Inside the loop. I guess it's technically a loop. Inside the loop partition 1 is calculated as the midpoint of left and right. This represents the numbers. It represents the numbers. Yeah. So we have the first partition. First partition will be the middle of left and right always, and the second partition will be the remainder between that point and the halfway point. Because when we have two arrays, we want them to what do we want them to do? We want the half, or we want, yeah. So no matter what, this position will always change, but we want the remainder because the median will always be at the half point. So as this gets smaller, as middle gets smaller, or as partition 1 gets smaller, half needs, or partition 2 needs to get bigger. So partition 1 and partition 2 will always equal half. That's fine, I get that. Left 1 and right 1 represents the element just before. Yep. If a partition is at the very beginning or end of the array, yeah, okay, that's fine. If the loop checks if the current position is valid or ensuring. And then you binary search. Ooh. Let me think about this. Maybe I can think my way through the left less than or equal to. No, I don't get it. Why does the binary search have the binary search? Binary search is conducted on all indices of the first array. Starting with left equals 0, right equals length 1. Oh, wow. That makes so much more sense. So if the median's here, oh, I see. It's because we're searching for the median, basically. Wow, that's crazy. Okay, let's write it one more time. This makes so much more sense now. Okay, that makes a lot more sense. If okay. So we're getting two values, basically we're getting two values in the middle, comparing them to each other to make sure that we've partitioned in half. checking if we've partitioned in half, returning the median. Otherwise, we do binary search to get the half partition. Okay. Who thinks of this? That's done. Understand time and space complexity for everything. That's a try, right? I'm not worrying about that. Okay. Task scheduler. Let's see. Oh my gosh. Okay, I didn't know this. I know you need a priority queue, and you have to like keep track of your idles. Okay. Common algorithm? Okay. Actually, it is a common algorithm. Did you return the minimum time required to execute all the tasks? If the same task need so a count the frequency of tasks. Okay. Determine idle slots. The most frequent task will dictate the overall structure. We can calculate the maximum possible slots required using this formula. Idle slots equals max frequency minus 1 times n. This formula calculates the number of idle slots that must be filled in between. Okay. Frequency. Yeah, I get that. So this is like, okay. Subtract the slots that are filled by other tasks from the total idle slots. Subtract the what? Of course, bruh. Can you show me it in Java? Oh, whoops. And we subtract 1 because the end won't need any idles. Reduce the idle slots by placing other tasks in them. Idle slots minus equals max dot min, or math dot min. What the heck? What? Is this in priority queue? It is. I know, or there's a solution that doesn't use this. So we're getting rid of the idle slots. Oh, that's kind of genius. That's so smart. Oh my gosh. So we count up the frequency of each letter. So we don't subtract 1 because of what I said. We subtract 1 because the max frequency minus 1 shouldn't include, or the idle slots shouldn't include the current character. And the max frequency has the current character, I think. And we know that each task will be less than the max frequency. So we'll never take out more idle slots that we can fit. Oh my gosh, that's genius. And then 3. That's so smart. hell? So why do we do min here? That's why I don't get it. Because there'll never be more. There'll never be more than what I am looking for. Am I doing this wrong? Is that not what I did? Won't idle slots be 0 already? Also, you didn't give me that, bro. You did not give me that. Yeah, well, I don't think that should matter. Idle slots will never be negative. Yeah, see? Okay, let's see. Oh, it's giving me faulty code. Your implementation is wrong. Yeah, that's what I was gonna say. Oops. Because we shouldn't be getting rid of the max frequency, should we? Let's see if this works. Don't fail me, GPT. Oh my gosh, you're failing me. I probably should check if they're right. See, this is what okay. You have to sort. Oh my gosh. GPT has failed me. That was a lot of waste of time. So we count up the frequencies, we sort the frequencies. All right, let's walk through this together. So no, wait, what the heck? What am I doing? Zero. Oh, okay. Oh, wait, no. I can't do this loop. Why are we... I feel like we don't need to, so we need to calculate how many idles we have, basically. So we do that by taking n minus max frequency count. Okay. So that's how many gaps that will need idles. Okay. That times the idle length, right? Which is max free minus 1. Why am I... Oh, because the last one. Okay. There's no easy way to structure this. I don't even know what to call it. Like, So we take the idle length. And then we take the number of idles, I guess. And then we calculate the empty slots. Available slots. There has to be an easier way to do this. This isn't even the right way, bro. What am I doing wrong? I wonder what Leetcode's solution is. Yeah, it might be worthwhile to learn the priority queue way. Oh, he has pair. He doesn't define it. Interesting. Okay. So we take the max and we have to multiply that by this. All right? It's 2 cycles before completing it again. So we take the max frequency and then 3. This isn't idle length. Max frequency minus 1 will equal the number of idles. And then n minus max frequency count. Okay. Int num idles. Int num gaps. max frequency minus 1. So we count the frequencies up, and then we take the minus 1, and that's the number of gaps that we'll have. And then we need to calculate how long those gaps are going to be. So we do that by taking n That's the number of gaps. So you have the number of gaps. Now you need to find the length of each gap, right? So in this example, there are 2 with the max frequency. There are 2 tasks with the max frequency. So it'll be 2 minus 1, which is 1, and 2, which is 2, minus 1, which is 1. So, but that's not the number of idles. There are 2 idles. Max frequency is max frequency minus 1. That's how long each idle is going to be. Like we have a potential idle and another potential idle. Okay, instead of this, I'm going to do cool down time. Cool down length time. Okay, so this is our cooldown time. The most frequent task. Is it? Wait. Yeah. Oh. Dude, this is so complicated. For no reason, too. Hey, max frequency is 3 minus 1. But n is the cooldown time. We already know the cooldown time. What? Max frequency. What does max frequency minus 1 tell us? Okay. Oh my gosh. Can you rename the variables to something that makes more sense, please? Okay. Cancel. Gap count, total slots per gap. So max frequency minus 1. Okay. Maybe I did have it right. So when we have the max frequency, that means we know how many times we need to cool down. So in cool down count is max frequency minus 1. Okay, that makes sense. Idle slots per gap. So int idle slots per gap. So we need to calculate n minus max frequency count minus 1. See, how does that get us how does this get us idle slots per gap? N minus max frequency task. Okay. So we have the count of we have the number of tasks that share the max frequency. Okay. So if we have multiple tasks that are the max frequency, then our cooldown is effectively less. Okay, so this is our new cooldown time. Okay. That's our new cooldown time, which makes sense because every time we encounter a task that has the same frequency as the max frequency count, it's effectively reducing the cooldown time for that task. Okay, so that's done. Int cooldown count, cooldown length. So we have the cooldown count, we have the cooldown length. Now what? I shouldn't have gotten rid of those. There we go. Cooldown count, cooldown length. Yeah. So the cooldown count times the cooldown length will get us the number of cooldown slots. The more I think about it, I just get more confused. Max frequency -1. Is that really the cooldown count? The amount of times we have to cool down. So we cool down that many times. Okay, yeah, actually that makes sense. Cooldown length. Okay, I think I'm overthinking this. Cooldown slots. So cooldown count plus cooldown count times cooldown length is going to be, that's going to be the maximum amount of slots that we have to cool down. Because that doesn't take, so cooldown slots, if we, this calculation doesn't take into consideration anything that isn't the max frequency, any task that doesn't have the max frequency. So max frequency times max frequency count. So this is the number of guaranteed fill slots we have currently And then this is the number of tasks. So this will give us the remainder. This will give us the non-max frequency slots. Tasks remaining. So these are our remaining tasks. Cooldown slots minus the remaining tasks. Why do we... Why do we do this max calculation? Okay. Okay, so we have all the mnemonic variables you could ask for, except for this. So we calculate the number of times we need to cool down. We calculate the length of time we need to cool down for. We calculate how many, the total amount of cooldown slots that we have. Then we calculate the remaining tasks. If you take the cooldown slots and subtract the remaining tasks, you will get the remaining cooldown slots. But what happens if remaining tasks is greater than cooldown slots? Does it just tack it onto the... So this is going to be remaining idles, by the way. Can you explain this, please? Can you give me an example where you will have more remaining tasks than cooldown slots? A, B, 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 C, C, D, D, E. Okay. Max frequency is 3. I need to ask it to... I need to ask it to refactor. It's... Can you refactor your explanation to this, please? Okay. Okay. Cooldown count. Okay, so frequencies. Max frequency is 3. Max frequency count is 2 because A and B both have 3. Cooldown count. Cooldown count. Okay. cooldown count. I feel like this can be renamed to something better. Num cooldowns. Num cooldowns. The number of cooldowns times the length of cooldowns. Number cooldown count. So the number of cooldowns times the cooldown length. Cooldown count is the same thing, and honestly, the variable name looks a lot better. So take the number of cooldowns, multiply it by the cooldown length. Cooldown slots. So the number of cooldown slots is going to be 2. The remaining tasks is going to be 6. Because we have C, C, D, D, E. A, B, B. A, B. How do we take that into account? Remaining idles. How do we take into account that we have gaps to fill those? Because it's going to be A, B, idle. Actually, let's just copy this over. It's going to be it's going to be A, B, idle, A, B, idle, A, B, idle. C. So then we can do C, 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 D, and then E, D, E. 6, 7, 8, 9, 10, 11, 12. Oh my gosh. Okay, how does the algorithm know that though? Wait, no, that's so wrong. Yeah, this is wrong. How does it know that you can fit so at the end of the day, we're gonna have A, B, idle, A, B, idle, A, B, idle. So we know we can throw in like a C here, a C here, and a D here. But how does it know we can throw in No, that's not how it works. It's C, D, and then E, and then what it does is C, D, E, and that satisfies it. But how does it know that? It has to do with something with the remaining slots. doesn't even do that. How does the algorithm know that you can fit C, C, D, D, E, E in the remaining spots without breaking the cooldown condition? The algorithm revolves around placing the most frequent tasks first. Yes, I understand that. Two gaps. Yep, 1, 2. Length of each gap is 1. Because this B would be there. This B would be there. Yep. That's crazy. So because we got the most frequent, nothing else needs gaps? So as long as we calculate the necessary number, as necessary idle slots for the most frequent values, we can guarantee that the most frequent values have a place without violating the end rule. What's the proof? The key inside of the algorithm. Mm-hmm. That's crazy. Oh my gosh. This is the key. I don't even know how to explain how it works. Basically, we set the stage for this. And then because we've placed the most frequent values, we can guarantee that the most non-frequent values won't violate the n condition. Because, yeah, so it's basically like you place all the most frequent values, and then when you hit the non-frequent values, you can guarantee that they can be placed within n because there will, like, the remaining number of idle, or the remaining cooldown slots are enough to separate the non-max frequency values n times away from each other, and then anything remainder will have enough unique values to have a permutation where the end, so like this is the sorted portion, and then we can guarantee that this will have a permutation where E is at the end. That's crazy. That's crazy. Cooldown count, cooldown length, cooldown slots. That's wild. Who thinks of this, bro? Okay. Uh-oh. I'm actually gonna undo that and submit this so I have at least a reference. Yeah. Also, did I technically skip a day? Oh, no, did not mean to do that. What the heck? Never mind, I'll just click on it. No, I didn't. Okay, 5, 8, cool. That's kind of wild. Let's see if I can solve this. What did I name it again? I named it something. I don't think I named it idles. Remaining idles. I literally had it right here. Okay. That's tricky. I'm gonna have to come back to that. I'm gonna add this. Redo task scheduler. Yeah. That's interesting. Okay. I'm gonna do it one more time just to make sure I know it. I question whether or not these are named properly. These are flipped. This isn't. This is the amount of times we need to cool down. Wait, is it? No. This is. Okay, I have it right. Wow. See, this is still complicated. This is still tricky. I don't know why. Okay, that's done. Which do I want to do? Union find. I think I understand like how to do this. I think at the time I just forgot about union find. See, this is what I was talking about last time. You can structure the union find incorrectly and it'll still give you the right answer. Okay, so oh, I do not get this union find. Oh my gosh, this is making no sense. Okay, I think I'm gonna have to watch a video on this one. I'm gonna try to redo it though the right way. What? Whoa, what? Did I not do that? Is this not exactly what I have? Isn't that... Okay. Yeah, I'm gonna have to revisit the union find data structure. I think I'll add it here. Study everything about union. Yeah. Okay, so we knocked out what? How many did we knock out? Like 3? $20 an hour. There you go. So we got rid of a redo task scheduler. Say everything about union find. What do we have a day ago? Did I really only go through 2? I don't know about that. Did I? I mean, task scheduler took forever. Oh no! I went through the partition. I went through a few. I think there was 1 before partition. Okay, so I went through a few. Yeah, we're gonna have to keep on chipping away at these. Okay, so what are we at? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And these are the ones that are gonna take a while. Yeah. These will take a little bit more time. Dang. Well then. Okay. It's 11 right now, I think. Yeah. So we will we'll keep on going tomorrow. I'm happy with the progress I made in an hour 45 about. That task scheduler stuff was terrible though. I don't even know why. I'm probably gonna redo it tomorrow just to see if I remember it, and we'll keep on working on that. But yeah, cool. I think we're good for today. That was not too bad for the time we had. Sweet. Till the next time.